Okay, so welcome everyone to the LMS undergraduate summer school that this year is taking place at Swansea. It is my pleasure to introduce Professor Scalas, who will continue with this mini course on Monte Carlo simulations of anomalous random walks. Enrico, anytime you're ready.
Thank you very much. So I will try to, and yeah.
I think we have lost your audio. Sorry, I can hear you from very, very far. No, no, it doesn't work. And now I can hear you. Yeah.
Yeah, the microphone is not covered at all, but it is probably the internet connection that is not working very well.
Mm-hmm. So if you want to try to, I don't know, are you sharing a screen? If you want to
yes,
try
yes,
that,
sure. I will try.
Tell you, I'll find a way to tell you if the connection drops.
Yes, thank you very much.
Unless it's dramatic.
Yes, yes. And I will now try to share the screen as I did before. Share. Yes, so now you should be able to see my screen. And we go to the presentation and we make it full screen. Yeah. Okay, so as you see, I corrected this part here. And I noticed also a couple of other misprints in the next part. So we had seen how to simulate the calculation of the integral with Monte Carlo simulation, or how to compute the integral with Carlo simulations. And now we go to the inversion method or transformation method, illustrating it for the exponential distribution. So of course, if you have an exponentially distributed random variable x, its probability density function has only positive support, and it is given by lambda multiplied by the exponential of minus lambda multiplied by the argument u. Well, the argument name is a dummy name. Usually you can find here t normally because the exponential random variable has the meaning of waiting time between events, but it doesn't really matter. And this lambda is a positive parameter, a real positive parameter. Yes, so I did not put all the assumption lambda element of reals, lambda positive. I just meant positive, but now the corresponding cumulative distribution function is just 1 minus the exponential of minus lambda u, again for positive u. Right? And this in R can be simulated with a predefined function, which is this Rx function that you can see here. Now, we will move soon to the program and see it working. This line of code would generate 1,000 independent exponential random variables with rate lambda equal to 1. You can also use the inversion method. If u is uniform in 0, 1, then the minus logarithm of 1 minus u divided by lambda is an exponentially distributed random variable. So you can try to compute the cumulative distribution function of this random variable x. This is the probability of x being smaller or equal than a certain number. We use here the argument w, and then you replace the formula here, you manipulate the inequalities, and you remember that the cumulative distribution function for the uniform random variable is a straight line with essentially the diagonal of the first semi-quadrant for x between 0 and 1. And then if you use this, you get exactly where you wish. And so the following line should be equivalent to the previous one. Okay, let's see if this is true. And let's move to our, okay, so this is the program. And I have 3 ways of generating uniform from uniform random numbers the exponential distribution, or using the existing function that generate exponential random variable. Let me see if I made a mistake here. No, it's correct. So now let us see what we are doing here. We are defining in this line the number of pseudo-random numbers we want to generate. And we put this number into
Enrico, we might have lost you.
Thank you. So what about now? Can you hear me?
Yeah, now we can hear you. I think we have lost at least 30 seconds.
Yes, yes. So you probably lost me when I was defining lambda. And okay. And then now you have the generation of 10,000 uniform random variables. And then you use the transformation that we have shown before. So x1 should be 10,000 uniform random numbers, and then exponential random numbers with lambda equal to 1. Okay, that's fine. You can also use minus logarithm of u, because u and 1 minus u, because u is uniform, 0, 1 have the same distribution, essentially. The third possibility is you use the existing function, which is exactly what I was suggesting before. And now you can plot the probability density function and compare it with the simulation using histograms normalized with probability equal to true, as we were saying before. Okay, look here, I am just defining a vector of values from 0 to 10.5, just to illustrate the theoretical distribution. It can be done in different ways here, but, and then y would be the value of the probability density function in these points. Then I am plotting the histogram of x1. This is the transformation we were studying. And I am superimposing to this the theoretical values. Let us see if this is working by executing it up to here. Now, the histogram of the values that we have computed with our Monte Carlo simulation, it's a bar histogram, and the theoretical function, which is this solid line here, which superimposes to the histogram. And And then you can also plot the empirical cumulative distribution function using these codes here. So the empirical cumulative distribution function, you sort the random variables, you compute essentially the fraction of the sorted values, and you get an estimate of the cumulative distribution function. And this is the theoretical value, 1 minus exponential of minus lambda x, and you can plot again. Let me remove this plot and do the same here. Here now, let me move this a bit down. You see in this plot that the Monte Carlo simulation is represented by these circles here, and the theoretical value is represented by the solid line. Maybe again, as we did before, if I put the color equal to red, I should be able to see the theoretical values better. Maybe it's col and not color. Maybe I just write it lines x w in col equal red. And let's see if this is not working. I will have to look. No, it is working. And now you see the red line. You can see it better now. It is superimposing quite well with the Monte Carlo simulation. And so you get, of course, you can improve this plot by using logarithm scales, etc., to look for deviations, or even better, instead of plotting the cumulative distribution function, you can plot the complementary cumulative distribution function to highlight where there are fluctuations, and then but the comparison is reasonably good, I would say here. Every applied scientist would be very happy to see such a plot where the experimental points are superimposing to the theory in this way. Of course, here we are expecting that because we are doing Monte Carlo simulations, but however, which tells you another application. In many cases in probability theory, you can get some nice formulae for some random variables, etc., etc., and then you can check that these, for instance, these formulae are correct by running Monte Carlo simulations. It's an independent check that you can run, and it's another reason why Monte Carlo simulations are useful. Also, from this kind of analysis, you can derive goodness of fit tests, limit values, if you want to do this kind of business. But I am not going to present all that to you today. Rather, I would go back to the presentation, see if I can share it full screen, and move to the exercises. So I've not presented a real exercise sheet, but at the end of each of the first 4 presentations, I am suggesting some exercises for you that you can try to work out in case you have spare time and you like programming. And in particular, I have this question here: starting from a uniform random variable in 0, 1, how would you simulate the following 2 experiments? The toss of a coin and the throw of a die. In other words, the exercise is asking you to write a Monte Carlo simulations of these 2 experiments, which are prototypical random experiments, even if, yeah, you can find, for instance, papers by Percy, Diaconis, and co-authors related to the real randomness of throwing dice and tossing coins. In fact, in principle, these are physical phenomena following the laws of classical mechanics. So if you know the initial conditions of your system, you should be able to have a deterministic result when you, for instance, toss the coin. Well, it's an interesting point, but there are good reasons in many regions of the phase space of these experiments to claim and expect the classical randomness, in which you would expect that each side has a probability of getting there of 1/2. But many things can happen. For instance, if you are good enough and careful enough, and this is used by conjurers and also cheaters, you can make the experiment in a way that you end up always with the face you wish to end up. And I distinctly remember, you would not believe me, but I succeeded in doing so. Once I tossed a coin and it ended up straight ahead on the... I could not believe myself. I should have taken a picture of this experiment. The second exercise is on Bernoulli random variables, and we will need it a bit later when we discuss the random walk. What is a Bernoulli random variable? Is a dichotomous random variables assuming only two values, say 0 and 1, and with parameter p, where p is the probability of getting the value 1. And now my question is, what is the expectation of the random variable and what is its variance? And then using your program for a coin toss, can you generate a sequence of any independent and identically distributed tosses? Then you assign the value 1 to the outcome t and the value 0 to the outcome h, and you consider the sequence of values that you get. So this would be a sequence of the zeros and ones. And you want to compute this number here. This is the mean, the sample mean, and this sample variance here. What happens to these values for increasing sample? Yeah, if you are already familiar with all these things, this is leading you to understanding better the meaning of laws of large numbers, and in particular the strong law of large numbers. So I hope you could follow me up to now. I do not see any question in the chat. So I can move to the second part of my presentations. I'll just go to the second presentation, share the screen again. Sharing the full desktop. And before starting this presentation, there is just a reminder that we are trying to understand the evidence necessary to read this paper and understand what's going on in this paper. And this paper is about a particular kind of process called continuous time random walks by applied scientists, in particular by physicists. And so one of the ingredients of this process is the random walk. So what is a random walk? And this is what the second presentation is about. So we will define the random walk and discuss some of the properties of the random walk. In particular, we will focus on how to find the cumulative distribution function of a random walk and the corresponding probability density function of the random walk. And then again, I will propose some exercises for you to try for tomorrow or the day after tomorrow. So this transparency, this view graph is devoted to a definition of the random walk where the elements of that we are going to sum in the random walk have an arbitrary distribution. So you have a sequence of independent and identically distributed random variables, xi from 1 to infinity. And because they are identically distributed, you are interested just in the distribution of x1, and the distribution of x1 will be the distribution of x2, of x3, and so on. So they will all have the same distribution. So this distribution is characterized, for instance, by the cumulative distribution function, or equivalently by the complementary cumulative distribution function, which is 1 minus fx1 of u. This is the probability that the random variable is smaller or equal than a certain number u, and this is the probability that the random variable is larger than that number u. And then you can introduce the probability density function as the first derivative of the cumulative distribution function. Now, of course, we are assuming here that the probability density function is existing, but we will be mainly concerned with two classes of distributions. So those distributions that are continuous, from minus infinity to plus infinity, and those that maybe are not continuous but contain a countable number of jumps in f, which is then represented by a comb of Dirac's deltas in the density. So with using these kind of distributions and with a proviso that this object here can be singular and be represented by a Dirac deltas distribution where there are jumps in the cumulative distribution function, and the delta is in the point in which there is the jump, and it is multiplied by the width of the jump. With this proviso, we can always use this notation because the jump will be represented by a theta function, and its derivative formally is a delta. Okay. If you do not know Dirac deltas, don't worry. I mean, just assume that this is a continuous distribution and you will be able to follow me without any problem. And now let's take a positive integer larger than 0, so it can be 1, 2, 3, whatever, and then consider this random process defined by sum from 1 to n of the xi's. This object here, Zn, we call random walk. So the random walk is a sum of independent and identically distributed random variables. You see that it is related in a sense to the sample mean, where here you would have as a random variable 1 over n. So it's n time, if you like, the sample mean. Okay, this is a formal definition of the random walk, and I see a question. Yes, so why it is called a random walk? It is called a random walk for this reason. If you start at 0 for n equal to 0, then you wait until n equal to 1, and then you will jump to x1. So x is sort of the width of a jump, and z is the position of a particle that is jumping at discrete times. Yes, so why this is a stochastic process or random process. So if here you have a sequence of random variables. If you fix the event, so you know which value the random variables are assuming, then this will be a function of n. On the contrary, if you fix n, this is a random variable. So it is a function of two quantities, one which I have not highlighted here, which is the omega of your probability space. And the other one, which is highlighted here, is n, is the discrete time at which events are occurring. And so because you jump of a random quantity and you move on a line, suppose you start at 0, after at step 1 you will be in x1, at step 2 you will be in x1 plus x2, at step 3 you will be in x1 plus x2 plus x3, and so on. That's why we call this a random walk. If this is a Bernoulli random variable taking values, for instance, in 0, 1, you have a similar representation, and then you have that sometimes you get this random variable equal to 0 and you do not move. Sometimes you get +1 and you jump up of 1. And now suppose this is again a random variable with two possible values, +1 or -1. You start in 0. First type, you flip a coin, which can also be biased, but let's say it's unbiased. With probability 1/2, you go to +1. With probability -1/2, with probability 1/2, you go to -1, and with probability 1/2, you go to +1. Then suppose you are in +1, you just flip another coin. You can go to +2 or back to 0, etc., etc. And this is probably the random walk that you are used to, the one with +1 and -1, where these xi's are +1 and -1. Here we are allowing x1 to take any real value from -infinity to +infinity. I don't know if this is answering your question. Why is it called random walk? Giovanni, is it answering your question? Yes, thank you very much. Okay, so let me share the screen again. And go back to the presentation. In fact, some examples. Oh, another question. Oh, thank you very much. No, it was not a question, but just a comment. Okay, great. So here are some examples. One example we were discussing just before. You have a Bernoulli random variable, which is 0 with probability 1 minus p, and 1 with probability p. And then your probability density function is a mixture of two Dirac deltas. And one is multiplied by one minus p, and the other one is multiplied by p. And what happens to another case in which you have positive random variables? So you have a density in which the random variable is exponential. You can do that. You flip an exponential point, or you apply the transformation that we have done before. You get a sequence of those random variables, and you start summing this sequence using cumulative sum. Well, let's try this case since we have a simulation of the exponential random variable. So example 2. I will take the risk of simulating it with you. Maybe I open another document. And we start, we start from the sample size, but this time, let's simulate just 10 random variables. Good. Now we use the built-in function. But we have to set lambda, for instance, to 1. Why not? Okay, so here we would have a sequence of 10 exponential random variables with lambda equal to 1. And now it is very nice because our z would just be the cumulative sum of x3. Oops. And if I run this, I see what I get. You see, this is the initial value. Then I have the sum of these two first values, then these three values, etc., etc. And this is a sum of exponential random variables, which is very nice. And now what I can do is maybe add also 0, but it is not so useful. So let's, for instance, plot z, and maybe with a stairs plot. Just to illustrate your random walk. So you start from 0, which is not represented here. Then you jump here, then you jump here, here, etc. So this is your z as a function of the index. And we can also superimpose the points in which you have these variations. Remember, this object is defined only for discrete random variables. Of course, you can make this continuous. And for instance, this is a possible interpolation. You have another possible interpolation, and many other, in fact, which is with lines. Okay, so this is exactly the same plot as before, except for the fact that now we are interpolating with a straight line between the points. And the difference between these two representations of the random walk, if you take them seriously, is that this is a continuous function, whereas the previous one had these jumps, vertical jumps. So it continues almost everywhere, but flat, except in the position of the jumps. If you are careful in defining what happens after the jump and before the jump, you get a function which is called with a French acronym, CADLAG, which means right continuous with left limit. So in French, it would be continue à droite, limite à gauche. Yes, so this is an instance of random walk related to example 2. Actually, it is somehow a simulation of example 2. Okay, let's see if I can. Yes, beautiful. And you can try the same with normally distributed random variables with parameters mu and sigma. And the density would be this one. Now, for instance, suppose we want to know what happens after 10 steps. So what is the distribution of this value after these steps, after 10 steps? Of course, I can run another Monte Carlo simulation if I find the file, or just another x3, another z, another plot. You see, this gives a different realization of the random variable and a different final value, and so on. So I can do it another time. This time, let me show you maybe more. Okay, maybe I can move it like that. Beautiful. And if I press return, you see that this is changing. And I can go on forever. Getting different realizations of the same random process and different final values for Z10. So what would be the distribution of this random variable? Well, luckily, we can use some results to get info on what is going on after n steps for the random walk. First thing is equation 2, which is giving us the expectation of the random walk. The expected value of the random walk is just the sum of the expected value. Remember that the xi's are independent, and here it's not important, but they are identically distributed. So all these values here are equal to the expected value of x1, and you're summing them n times, so you have n times the expected value of x1. So in the case of the if you want to know what happens to Z10, you can apply this equation 2, you multiply it by 10, the expected value of x1, and you get the expected value of Z10. And you can get very easily also the variance of Z10. You compute the variance of the sum of independent and identically distributed random variables. You apply the formula for the variance of the sum. And because these are independent random variables, but it would work even if they were uncorrelated, but these are independent, so the covariance is 0, so it is the sum of the variances. And again, all these variances are the same, and you get n time the variance of x1. So already using some elementary results from probability theory, you get information on the expected value of this random variable Z10 and its fluctuations. But you can do more, in fact. You can really compute exactly, meaning analytically, the distribution of Zn for any n. You just have to remember that the sum of two independent random variables has a distribution that can be computed, and this is indeed the convolution of the distribution of the two random variables. Yeah, I mean, there are different ways of getting this result, but this is one. You compute the cumulative, you look for the cumulative distribution function. This means the probability of x plus y being smaller or equal than z, and then you use here a relationship between probabilities and indicator functions. So the expectation of an indicator function of a set is the probability of the set. So using the expectation and using then some clever representation of the set x plus y smaller than or equal than z, you can write the expectation explicitly, and then you remember that the two random variables are independent, which means that their joint density factorizes, and then you use this fact to get this formula here, which is essentially giving you the convolution of the two measures of the two cumulative distribution functions. You take a derivative of this object with respect to z, and you get the convolution of densities as the density of the sum of two independent random variables. And then you use this again and again, but you can also use the method of characteristic functions to deal with independent random variables. If you have an independent random variables, the characteristic function is nothing else than the Fourier transform of the probability density function. This is the expectation of the exponential of ikx, actually kappa. I am using the Greek kappa here. What is the characteristic function of the sum? Well, it is the product of the two characteristic functions. By the way, equation 6 gives also you a proposition that the characteristic function of this convolution is the product of the two characteristic functions of the two random variables. So, as a consequence of the previous results, by applying this formula again and again and again, you find that the cumulative distribution function of Zn is the n-fold convolution of the distribution function of x1. The density of the Zn is the n-fold probability density, the n-fold convolution of the probability density function of x1. And the characteristic function of Zn is the nth power of the characteristic function of x1. In particular, equation 9 is very convenient because you don't have to compute integrals as you would have to do with convolutions. You just make products, and you hope your nth power of the characteristic function of x1 is a function that can be a Fourier transform that can be inverted back. But even if it is not possible, and get an appreciation of the densities, numerical evaluation of the density of the sum. So using convolutions and the fact that you are summing independent and identically distributed random variables, you get to this beautiful relationship, which it gives you a full information on the density of and the distribution of a sum of independent and identically distributed random variables. Let me conclude this presentation with two exercises. This is very instructive. You can try to make these calculations in the case of the normal distribution. Let's take mu equal to 0. So we consider the symmetric normal distribution and try to compute these three quantities here. You will find a surprise if you try to do so. And this is not simulation, but now we already did it in the lecture, but you could try to write a Monte Carlo simulation of the random walk using exponential random variables. We have already solved this, but you can try to modify what we have done by studying the normal random variables with mu equal to 0. And it is interesting to see what happens in case 1 when lambda goes to infinity, and in case 2 when sigma goes to 0. And I believe we are almost 10 minutes before the end, so I have to stop here in order to start the discussion. But before stopping, the second ingredient that we are going to discuss tomorrow morning are renewal processes. So I believe that many of you were already familiar with random walks. I'm not so sure how many of you are already familiar with renewal processes. But for sure, you have already seen an important instance of renewal process, which is the Poisson process. Let me ask you, how many of you have already studied the Poisson process in your probability courses? You can raise your hands and then I go to the messages. I see many hands, 6, well, many, 7. I will wait a few seconds more. And how many of you have already seen renewal processes? Let's stop with the Poisson and let's go to the renewal processes. 5 of you. It's yes, it's Poisson. Yes, so the surname of the mathematician means fish in French. That's nice fun. So 3 of you already are familiar with renewal processes. Okay, you will see the idea of renewal processes is a simple generalization of the Poisson process. Giovanni is asking if I have any suggested reading to catch up for tomorrow. Yeah, I mean, why don't you go to why don't you go to simply to Wikipedia and look for Poisson process on one side and renewal process on the other side and check what is written there. Why not? And if you don't like Wikipedia for any reason, you can look at maybe just some. Let me share the screen again. Here, so for instance, Poisson process. Okay, so I find Wikipedia pages on probability. I mean, they are not ideal, but they are not bad. And if you don't like this for any reason, you go on here and you find videos in YouTube. I mean, I cannot vouch for these videos, but sometimes they are very well done. And then, okay, I mean, the Massachusetts Institute of Technology is offering you an introduction to the Poisson process that you will find immediately. And you will find also some of the equations we are going to use tomorrow, if you want to read and catch up. I mean, it's not really necessary because I am introducing everything you need step by step, but it's not a bad idea. Okay, let me stop sharing and go back to see if there are other questions or comments.
Well, let's. I'd like to thank you, Enrico, before we move to the question. So let's thank Enrico for the fantastic lecture, and we look forward to tomorrow ones.
Thank you very much.
I'll stop now the recording, and we can informally discuss.
Very good.